for this big question. It isn't okay. The final examination maybe the 40%. Okay, you have any question? What is a experiment? Okay, experiment just during the course, I just give you the experiment, the task. Maybe just, for example, let you to write down some code to implement some the truth table, for example. But don't worry, that means I just give you the how to do it, but you should to implement it by yourself in your favorite the programming codes. Okay. The idea I will give you how to implement, but you just your work is writing your codes in your private uh, codes, okay, to implement this. Okay, if you have any other question, I'll just move on the next. And from this next, we just using the online this video. Maybe it is very clearly to listen about it. So for during the time you have any question, you can just put your voice and sometimes you can raise your hand online.
Section will covering propositional logic. Welcome to NA 315 at Bowdoin University, Discrete Mathematics. We are using our Wilson text, and this is chapter 1, the foundations, logic, and proof. And in this section, we're covering propositional logic. So before we get into section 1.1, just a general introduction about what discrete math is all about. It's essentially a part of mathematics devoted to the study of discrete objects. And discrete, basically, this means they are countable. So I can list them, I can count them, etc., as opposed to continuous objects like we dealt with in calculus. So examples of discrete objects are integers, steps taken by a computer program, which is quite often by discrete mathematics taken by those who are going into word-based fields. It basically is your foundation for the rest of the classes that you are going to need throughout your study at the university. On this slide, I just wanted to give you the basics of the kinds of problems that we might solve with discrete mathematics. So some of these we will look at this term together, and some we will not. And essentially, it opens the door to a lot of different areas. Obviously, the study of mathematics, and all of the things that we're going to learn, logic, set theory, probability, towards time. All of this is dealing with discrete math. For those of you going to computer lab, obviously it's a foundation for computer architecture, that structures, programming, etc. And you can even find some of the applications of discrete in other areas of study as well. So, section 1.1, propositional logic. In each section, I provide a summary for you. Essentially, I do that so that it's easier for you as a student to go back to your notes and find exactly what we covered in each of these videos. So a proposition is a declarative sentence that is either true or false. The notice made of green cheese, obviously this is a false statement. Trenton is the capital of New Jersey. Toronto is the capital of Canada. 1 plus 0 equals 1. 0 plus 0 equals 2. Again, some of these are true, some are false. I'll let you determine which ones are which. Examples that are not propositions include, for instance, sit down, or what time is it, or the two equations that I have written for you. Now, I want to talk to you a little bit more about those equations, but before we do that, I want you to have a chance to think about why they are not propositions. When we come to a slide where the title is written in blue, and it's PR1 or 2, meaning practice 1 or 2, in front of it, this is where I would really like for you to try the question on your own before I give you the answer. It's really important for students to actually try to think through these things before the answers are just given to them, because it doesn't require any struggle on your part to do that. So when we get to one of these blue questions, blue slides, I ask that you press pause, try the question, and then once you've either completed the question or you just as far as you are able to get, then you press play to see how you did. So if you haven't already, please press pause, and we'll get started in just a minute. So hopefully you did press pause and you tried the question yourself. So I have two questions actually in this slide. The first is, why are C or D neither true nor false? And in this case, we're looking at our equations. And so in question C, and in question D, I have many variables. So in question C, just one, and in question D, it's all variables. So why are they neither true nor false? It's because we have not yet assigned a value to the variable. So why are they not? Because it could be true depending on what value I put in. It could be false depending on what value I put in. So how do we make C a proposition? Assign a value. So if I said x equals 3, now it's a proposition even though it's a false one. If I instead said x equals 1, still a proposition, now it's a true proposition. So let's start constructing propositions. And we have propositional variables. And just like in algebra, it doesn't really matter what you use, but most often you use x and y. With propositional variables, it doesn't matter what you use, but quite often you're using p, q, r, s, etc. Now, the difference between a propositional variable and a variable that we use in algebra is in algebra, the variable represents a value or a set of values, whereas in discrete mathematics, a propositional variable represents those statements that are either true or false. Now, if we have a statement that is always true, then it's okay for us to denote it with 18, always true. This proposition that's always false is obviously denoted with false. And a lot of propositional statements might be true or false depending on the value or something else occurring in the problem, just like we looked at those equations a few moments ago. Now, compound propositions can really start to get confusing, so I would encourage you to spend some time just taking notes on these, or maybe making yourself a table to keep track of everything, but these are the compound propositions that we are going to be looking at in this course. So let's take a look at our first one, which is negation. The negation usually I have that in orange, but negation of a proposition, note the notation that we'll be using, and we say that not P, and it says, oh, hey, by the way, there's a truth table. Well, this is probably the first time you've seen a truth table. So let's talk a little bit about it before we look at the values. In a truth table, each row has all of the possible truth values for the proposition P. So obviously, with just one propositional statement, that statement is either true or false. So this is row one, and this is row two. Each of them represents a different scenario. So what the truth table says is if P is true, then the truth value of not P is false.
Hello? You cannot hear clearly? Maybe it is outside some noisy. Don't worry, this just the voice. We have the online version. I will just publish this online version on the WeChat group. Okay.
Whenever P is false, the truth value of not P is true. So we're looking by row. So an example, if P, remember P is a propositional statement, and we say that statement is the earth is round. So that is a statement that is either true or false. Obviously it is true. Then not P denotes that basically that it's not true. It is not the case that the earth is round, or most of us write that a little bit more simply, the earth is not round. So again, here we arrive at a practice question, practice 2. And the question is about connectives and negation. So my question is, are A, B, and C, are each of those propositions? If the answer is yes, it's a proposition, I would like you to find the negation. So I'd like you to press pause, try all 3 questions, and then press play to see how you get. So for A, my dog is the cutest dog. That is certainly a true proposition. But if I were to negate it, then I would say my dog is not the cutest dog. Or in quite a few of our textbooks, you would see it is the case that my dog is the cutest dog. But we just write things systemly as we can. Discrete math is the hardest class you will ever take. That is a proposition. I will let you determine if that is true or false. I'm going to guess false. And the negation, discrete math, is not the hardest class you will ever take. So we're just negating it, or changing the sign. Same thing, if I started out with discrete math is not the hardest class you will ever take, the negation would be that the discrete math is the hardest class you will ever take. And last one, is class over yet? Obviously, this is not a proposition. It doesn't have a truth value. So we have a chance to talk in a little bit of detail about the negation. But we also have other operators that we call connectives that are conjunctions, disjunctions, implications, functions, and by conditions. So over the next several slides, we're going to look at each of those in detail. So let's take a look at the conjunction. The conjunction happens between 2 propositions. And I want you to think back to when you learned about set theory, and then you had A union B, you had A intersect B, And it's really kind of the same. And it's really kind of the same idea. So notice this one would kind of be like this. Whenever we looked at A intersects B, we would always call that an and question. Well, that's what we're doing here. So when you see that, we're going to say it P and Q. And let's take a look at this truth table, because this truth table is a little bit more complicated than that last one again. So in this truth table, notice that on the left here, I have quite a bit more going on than before, and here's why. In our previous truth table, I only had one proposition, so there was only one way that can happen. So it works. Now I have two propositions. So it could be that P is true and Q is true, or P is true but Q is false, or P is false but Q is true, or P is false and Q is false. So in terms of the result over here, which is P and Q, what we're looking at is for both of them to be true. So as we can see in row 1 here, P is true and Q is true, and so that has a true conjunction of the two, true propositions. The others are all false because they both have to be true in order for the conjunction of them to be true, and obviously we can say that that's not the case for any of the other rows. So as an example, let's say P denotes I'm at home. Q denotes it's raining. Those are both propositions, they both have true values. We don't know what the true values are, but it doesn't matter. Then P and Q denotes I am home and it is raining. I typically stick with this one. I know some people can go into the buts, and it just makes it more complicated. So now let's take a look at this junction. For this junction of a proposition, again, I want you to think about that A union B, same kind of idea. We're saying, hey, we're satisfied if either A or B is true. Same idea here. We're saying P or Q, so we're using that word or when you're saying it aloud. And again, let's take a look at the truth table. I want you to notice on the left-hand side, this looks exactly like the truth table for P and Q, because again, these are the 4 different possibilities for the 2 propositions of P and Q. Now, this column obviously is different because now we're saying, hey, if one or the other is true, then we're satisfied and the whole statement, the whole disjunction is true. So notice here, we're both true, which means, yes, at least one of them is true. On my second row, P is true, so it really doesn't matter if Q is, because we've got at least one that is true. On my third row, Q is true, and therefore the whole disjunction is true. And then notice here, there are no trues. P is false, Q is false, therefore P or Q is false. So again, for example, we're still using at home and rating, then P or Q denotes I am at home or and it's raining. And again, or does have its own issues, and we're going to talk about those. So we've got this or in English, and then we have or mathematically. So there's the inclusive or. In the sentence, students who have taken CS 202 or Math 120, they take this class. So we can assume that students have taken one of the prerequisites, but they might have been able to take both. And that is what we're looking at in the disjunction. Okay, one or both needs to be true. However, when we're reading a sentence, soup or salad comes with the entree. Unfortunately, I can't have both soup and salad. I have to choose one or the other. So that's exclusive or, and that is the symbol that we use, and we say that excellent. So again, you can see the truth table here. This one is saying essentially that only one of them can be true. So notice here, one is true, and so I get a value of true. One is true, so I get a value of true. But this one that was true before is now false because only one of those two can be true. So hopefully that makes sense, the difference between or and excellent. The next one we're going to talk about is an implication. And an implication is obviously the meaning of the word implies. One implies the other. This gets a little bit trickier with the truth table, because we're basically saying if P, then Q. So again, this left side, this is nothing new. This is the same as we've seen before. But the if P, then Q, most people understand this one quite easily because if P is true, then Q is true. And most people understand this one quite easily because if P is true, then Q is false. Obviously, we want it to be true, and therefore the if P then Q is false. Because we're saying if P is true, then Q must be true. So this one is true, this one is false. But now let's look at the next one. So we're saying if P is false, well, what? Do we care what happens with Q? Well, no, not necessarily, because our conditional statement says if P is true, then Q is true. It doesn't say what happens if P is false. So since P is false, Q is true? Sure. If it's false? Sure. Because P was false and then false. So again, example, I'm at home and Q is it's raining, then if P, then Q says if I'm at home, then it is raining. So how does this work when we're looking at false ones? If I am not home, well then it could be raining or it could not be raining. Because it doesn't say anything about that in terms of essentially this is directional. So hopefully that makes sense because it's going to be another one that is not directional, but it's very important to keep those two separate. Cool, a little bit more on implications. Keep in mind that these implications, the if P, then Q, is all just based on truth values. It doesn't necessarily need to make logical sense in terms of real life. So if I've got, if the moon is made of green cheese, so the moon is made of green cheese is P, then I have more money than Bill Gates would be Q. So this doesn't make any sense, obviously. And whether or not the moon is made of green cheese in real life would have nothing to do with whether or not you have more money than Bill Gates. So we're looking just at truth values. If this is true, then this is true. 1 plus 1 equals 3, then your grandma wears combat boots. Again, those two things don't, it's hilarious. I'm going to see my grandma wearing combat boots. But it doesn't need to make sense. The P and the Q don't necessarily need to be talking about the same thing. But obviously, We have logical conditionals, and logical conditionals is where they actually sort of are related to one another. If I am elected, then I will lower taxes. If you get 100% on the final, then you are getting 8 points. So those are conditionals that are, you know, based on truth values, but maybe go together. So let's take a look now at some of the different implications that we have from an implication. Converse, the inverse, and the contrapositive. So the converse is essentially us switching the order of the two, if Q then P. Now, obviously, this is probably not going to have the same truth value or truth table as your original implication. Now let's look at the inverse. Inverse is if not P, then not Q. So notice it's the original order that I had P and Q, and I'm negating each. So that's what happens in the inverse is we negate each. So this one is switch order. This one is negate. And then the contrapositive is basically putting it all together. I'm negating and switching. So if not Q, then not P. Now what's important to understand is that truth table that we would make for the original implication would be exactly the same for the original implication and the contrapositive. It would not be the same for neither the converse nor the inverse. So, for example, if I'm looking for the converse, inverse, and contrapositive, it is raining as a sufficient condition for my not going to town. And you might look at this and say, well, what does that mean? So it's okay before you try to find any of the other implications to write it in a way that makes more sense to you. If it is raining, and this is P, then I will not go to town. That's Q. So now that I have it in a way that makes sense to me, I'm going to look at the converse, which is switching the order. So if I do not go to town, then it is raining. So all I did was switch the order of P and Q. Inverse, I'm going to keep it in the right order, but I'm going to change the values. I'm going to negate each. So if it is not raining, then I will go to town. So this one I changed to not. This one already was not, so I changed to I will. And the contrapositive, I switch the order and I negate each. So if I go to town, then it is not raining. Okay, now I have one of those for you to try. So I've given you the statement, Professor B is happy when you get your homework done on time. Now, this one might mess with your head a little bit. So before you try to do the converse, inverse, and contrapositive, at least while you're practicing, I suggest writing this in if-then form so it's very clear what is P and what is Q, and then writing the converse, inverse, and contrapositive are actually quite easy. So press pause, rewrite the original implication, and then write each of the other three implications. And then press play to see how you did. So again, the first thing I'm going to do here is I definitely want to do a rewrite. And the rewrite is if you get your homework done on time, then Professor B is happy. Now, a lot of people struggle with that because, look, this happens first in my sentence. But you really have to think about which property implies which other property. And it says that Professor B or that I am happy when you get your homework done on time, which means this has to happen first. You have to get your homework done on time in order for me to be happy. That's sad, but you get the idea. So now let's look at the converse. Before I do that, you get your homework done on time is P, and Professor B is happy is Q. So let's take a look. The converse, if Professor B is happy, then you got your homework done on time. The inverse, remember I'm negating. You would not get your homework done on time when Professor B is not happy. And the contrapositive, switch the order and negate. If Professor B is not happy, then you did not get your homework done on time. Hopefully you did very well on this. And that you get your homework done on time. Now let's take a look at biconditionals. So if P and Q propositions with the same truth value, that's important.
Okay, we have 5 minutes break. So just about the question about your sign in or check in, you can directly just contact with my teaching assistant. Okay, because this is just the setup by her. Okay, we continue.
Same truth value. Then we form the biconditional proposition or a by implication because we're still using those arrows. One implies another. But notice this arrow is a little bit different. This arrow has got a little arrowhead on each end. Now the way that we write that is instead of P then Q is P if and only if Q. So remember when you have an if with an extra F, that means if and only if. So the biconditional if P then Q has the truth table right here. And so remember, this is only going to be true when P and Q both have the same truth value. So here, P and Q are both true, so it's true. Here, P and Q are both false, so it's true. Notice the others, where P and Q have a different truth value, result in a false result on the biconditional of the truth table. So if P denotes I am home and Q denotes it is raining, then P, if and only if Q, denotes I am at home if and only if it is raining. I haven't looked much at compound propositions yet, although that will obviously be a huge part of this study as we're looking at truth tables and conditionals, etc. But notice that the same way that I could write P if and only if Q, I can write it in another way. And that other way, so notice here I'm saying P if and only if Q is equivalent to, and then I'm saying if P then Q, and then what's this one mean? And if Q then P. So essentially I'm saying these two things are the same. So if P then Q, we already found these values of the truth table from the previous slide. But now let's take a look at the truth table that would help us come up with the truth values for this compound proposition. So again, this first row is just showing the different values that the first two columns are showing the different values that P and Q can have. True, 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 false, false, true, false, false. And then we start actually coming up with the values. So these are things that we would have to then figure out. So the first one says if P then Q. So obviously this one is true because these values are both true. This one is false because this is if true then false. And then remember these are those two tricky ones because P is false, and so because it's one directional, we only care about it when P is true. So now let's look at the same thing. We're looking at if Q then P. So if Q then P would be true then true. This one would be true as well, again, because Q is false. This one would be false, because if true then false doesn't work. And then this one would be true because that first value in the implication is false. So now that brings us to this column right here. And this column right here, what we're saying is these two should have equivalent truth values. So let's take a look at why this is. This says if P then Q and if Q then P both have to be true. So this is true, and notice I've written true here. This one does not work because they're not both true. This one does not work because they're both not true. This one, they are both true, and therefore I get true, false, false, true. And that happens to be the exact same thing that I have in the screen. So I just wanted to point out to you that these are two equivalent things. So one of them written as a compound proposition, one of them written as a biconditional. So we haven't really talked explicitly about how to create a truth table, though we've seen quite a few examples. So I really wanted to go through how to create a truth table of the process that we go through. So we already kind of knew that we would need a row for every possible combination of values for the compound propositions. So let's say I was using P and Q, which is two of them. Then I know the possible combinations are true, 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 false, false, true, and false, false. So essentially 4 rows. Now, if I threw an R in here as well, well, then I would need a row for R, and 4 rows isn't going to do it anymore because I could have R as being true for each of those combinations, or I can have R as being false for each of those combinations, and therefore I would need 8 total rows. So what we're looking at here then is essentially having 2 to the n rows, where n is the number of propositions. So here where I have just PQ, that meant 4 rows. If I had PQR or 3 propositions, that was 8 rows. Then in terms of columns, let's say we are looking to into table for P and Q or R and not P. So we've got a lot going on here, and what I would need is I would need a column for P, and for Q, and for R. I would need a column for Q and Q. I would need a column P because not P is used over here. And then I would need a column for R and not P. And then of course I'm out of room, but my final column would be everything put together. P and Q or R and not P. So here I would have 1, 2, 3, 4, 5, 6, 7 columns. Also, it's important to understand what the order of operations is, or order of precedence is. And here we can see which order we would go in terms of finding a not, finding an and, then an or, finding an if then, or finding an if and then if. Compound proposition. And we're going to create this truth table together, and then we're kind of study step by step by step. But essentially, here is the compound proposition that we are going to create a truth table for. So I know right off the bat that I'm going to use a column for B and Q. And I know that I'm going to have 8 rows because it's 2/3, 2 things. And then there is 3 is how many different propositions you have. And 2 is because each of those values has true and false. Next, we're going to create a column for each compound proposition. So notice here, I've got a not R, and a lot of people really need to put not R. Yes, you do. Really need to put not R, even though it's just the opposite order. And then another is the Q. And then notice one at the very end is our final compound proposition, which is if P or Q, then not R. So that's our final solution of our thing that we use. again, remember we talked about 2 to the third for 8 rows. So now we have as many rows that are necessary and have all the combinations that we need. And now we're going to fill in the truth table for the conclusions first. So I haven't been doing anything yet. I haven't been doing anything. I said, hey, I need for these, I need all of the different combinations that could happen when two people are in terms of two patterns like that. True, true, false, true, false. Different people have different strategies for how to keep track of this and all of that. I tend to just try to keep it as simple as possible. Notice what happens here. First column of that formations and houses, and then I alternate the tools, the prices, into all the feeding area. So before we continue, what I would like for you to do is to press pause from right here and see if you're able to complete the rest of this truth table on your own. So let's take a look at the values. Again, cat and password and but let's take a look at the values we should have in the table. This column says P or Q. So sometimes if P is true or Q is true, and then it's outside. So here I've got true, that means this is true. And then here, this is true. The third row, again, P is true, it doesn't really matter if Q is, because I need to relevant to zero. Same thing here, this is true, because P is true. The next column is true because Q is true. So I'm looking at these two, and I've got these two true. I'm looking at these two, if I don't, I'm looking at these two. Don't. So that's that first type. And now let's take a look at our file. Obviously, this is super duper easy because it's whatever's in R, I'm just putting the opposite down. Cost, that's cost, that's and now, for my final solution, which is using essentially this, the both here, if the here, then makes one. So with P or Q being true, this not R needs to be true. So this one has to be false because this one we have true true, so that is a true. This one we have true false, that is F. And P or Q is true, then that is true. Again, this one must be true. This is false, this is true. And two falses, remember that's not tricky then, because the if formal statement is false and true. The if formal statement. That is my solution. Which I have doing here in the last slide. So this is the final solution. If the or you, then multiple. Of course, I'm going to have the opportunity to try one completely. And so this is that question. This is P or not Q, or if P or not Q, then P and Q. So obviously there are only two propositions, which are that means two square or pair ways. And look, she you should be using. So go ahead and do your entire truth table. And then press play and see and get. Okay, I'm going to get started so you can not that pause. Well, shame. All right, so now we're just going to have our four different rows because we have our four different combinations for our two dimensional statements here. Then I need to find for not here because as I'm looking at this first combination here, I'm looking at P or not Q. Then I need to know what not Q is. So I'm down here in the column. And here I'm looking at P or not Q. And so true and false gives me true, true and false gives me true, false and false gives me false. Either one of them to be true, and then false and true gives me true, because one of the two is true. All right, so now we have that. I'm looking at the solution to this one. P and Q. I look at P and Q, I need them both to be true. And the only place that I know true is all of the rest of the false. So that hopefully is a very easy goal to figure out. Here, I'm looking at if this, then this. So that is what I'm determining from my final form. And so I'm saying if this is true, then this one should be true. So if P or not Q is true, then P and Q must be true. And that's what I get here. This one, I start with true, but I end with false, and that's so good. So notice my answer is false. Here, I begin with false, and remember when I begin with false, this is going to be true. And then the last one, I'm starting with true, and ends up with false. That is bad, and so that is false. So this is my final values. So your assignments. Oh, so one of the things that we need to become very good at is to be able to read a sentence and turn that into a propositional logic statement. So when we do this, what we want to do is look at our question, such as if I go to Harry's or to the country, I will not go shopping. So our job is to then determine what statements are we dealing with. So I go to Harry's is a statement. I go to the country would be a statement, and I go shopping would be a statement. Now notice I'm skipping the not for now because I will take care of that not with the not symbol when I actually write it. So notice here I've identified that I'm going to have three propositions, P, Q, and R. I go to Harry's, I go to the country, I will go shopping. And then we have to look at the connectives that we just learned in our last section. So it might be a good idea So now I'm saying A is a knight. Well, B must be a knight because he's telling the truth. If A is a knave, then B must be a. I just got myself confused. If A is a knave, he's telling a lie, which means this guy must be also a knave. And same thing is going to happen here. Okay, so we haven't really figured anything out yet. We're just filling in values on the table. Then it says B says the two of us are opposite type. So if B is a knight, he's telling the truth, and this guy must be a knave. So we can see that this is knight, knight, which matches what I had over here, but this is knave, knight, and so this one's not going to work. Let's look at the next row. B is a knave. B said the two of us are opposite types, so he's lying. So this guy's a knave. This is knave, knave. This is knight, knight. These don't match, and they don't match what I started with either, so that row is not going to work. Then we take a look at the next one. If B is a knight, then he is telling us the truth, and A must be a knave. So we have knave, knight. Over here I have knave, knave, and therefore those don't match up, and that is not a valid solution. And looking at the last one, B is a knave. He's telling me a lie and saying that they're opposite types, so A must be a knave. So now I have knave, knave. Looking at this row or this column, I have knave, knave, and here I have knave, knave. Because it worked out the same for my original statement and after each of the other statements, that is the only way that this can work logically. I have another question I'd like you to try, and this one is straight out of your textbook, page 23, number 18. And for this one, just to give you an idea of how we could write a truth table to help us solve this. I did solve this one with a truth table, but don't feel like you are tied to that method. I'm going to read this question with you, and then I want you to press pause, and I want you to really take the time to try this question before you look at the solution. So when planning a party, you want to know whom to invite. Among the people you would like to invite are 3 touchy friends. You know that if Jasmine attends, she will become unhappy if Samir is there. Samir will attend only if Kanti will be there, and Kanti will not attend unless Jasmine also does. Which combinations of these 3 friends can you invite so as not to make someone unhappy? So for the sake of uniformity, if you choose to make a truth table, just use J for Jasmine attends, S for Samir attends, and K for Kanti attends. So go ahead and press pause. Try this question. Take your time on it. It might take you a little while. It might just be really easy for you and you get it right away. Once you're done, press play to see how you get. So what I did was I looked at all of the possibilities, because essentially what I have is 3 propositional statements, and we know that 2 to the third would be the number of rows that I need. So that's what I did first, is just to make all of the possibilities. Then for each one, I looked at the statements given to me in the question. So it says, if Jasmine attends, she will become unhappy if Samir is there. And so notice I wrote, if Jasmine, then not Samir. That is this column. Then I looked at Samir will attend only if Kanti will be there. And so if Samir, then Kanti. And then my last one, Kanti will not attend unless Jasmine also does. So then if Kanti, then Jasmine. And essentially what I'm doing is I'm doing it the exact same way that I did the last question, except on the last question, I didn't use propositional statements or letters. I just used knight and knave, but it's really the same idea. So without going through step by step with you, essentially what I was doing is I was looking for any rows where the 3 values were the same. So here, this one didn't work. I had JSK, and obviously this one was not S, and so we were done. Here I had JS, not K, and right away you can see we've got a problem using the information that's given. So one thing I should point out, because maybe I didn't make that clear on the last question, for the K values, I want you to notice here that K isn't involved in anything here. So notice all I did was I took the K directly over. And for the J column, I took the J directly over because I'm determining what's happening with S based on J. So the only thing that I'm figuring out in this one is what's happening with S. Hopefully that is clear. Same thing if I'm looking at the blue column, that if S then K. I'll start back up there so you don't get confused. So if I'm looking at the blue column, if S then K, remember J is not changing at all. And S is not changing at all. I'm just basically transferring those over from what I had before. K is changing because it's changing based on the value of S. So again, I continued that for all three of the different statements that I found. And so what I found at the end is that I could either invite Jasmine and Conti, or just Jasmine, or essentially I can invite no one. So this one worked out just fine. And we can see all of those sets of three are the same. I said we could invite Jasmine, Conti, and that is this row right here. Jasmine and Conti got to go, but Samir did not. I can invite just Jasmine, so J, but not the other two, and that's this row right here. And again, what I was looking for is each set of three to be the same. Last logic question. I want you to use whatever method that you guys best. So whether that is or just read it out, I use whatever method that you like best. That's fine. Get started. Let's take a look at our stuff. Let's just tell us that we also know words and terms that we and these are terms that you understand. And then we have words. And Williams states that he saw both Smith and Jones were together from the now, of course, we know there are three options. And so essentially, we pick them from Smith and Jones. So let's start with words. Williams is what is the sound and that means Smith and Jones are from the This is goes from Jones, and Jones says he didn't know before. So let's put work because people get in front of Jones and then know that they don't know. So Williams is not going to Smith is the killer, and these are Jones, Williams. Jones said to get people there, and he was actually going to so Williams said Smith and Jones did Williams needs to go work because so people them good. So Jones is this one goes with the term that means Smith and Williams are telling the truth. Smith says he was a friend of Jones and means to fight him. And Williams says Smith and Jones were with her the day before. There's two company for them. Therefore, it's very possible that Jones knows with her the day before and who was killed. all the basic for you. So what is that through? So what interactions and first design these things. So your assignment is to.
Okay. Now this is just we have online course. Okay. So the question time, maybe we have just 5 or 6 minutes. If you have any question, you can raise your hand online or just input your question in the info group or the WeChat group. Okay. Hello, can you hear me? Okay. Now it's discussion time. If you have any question, you can raise your hand online or just input your question. Okay. Okay. Okay, you have no question? That's for today. Bye bye.